So learning objectives for the segment: define the conservation of energy, define system and surroundings, and how heat and work pass energy between them. Define and use the properties of state functions. So we start with the first law of thermodynamics. These are a bunch of bookkeeping rules that tell us what happens, what things happen in the universe and what things don't. You can't win. That's the first law of thermodynamics. Let's make it more precise to talk about what we mean by meaning. Energy, what we mean by winning. Energy can't be created or destroyed, only changed in form. We are sort of leaving out nuclear reactions here where we discover that energy and matter are sort of the same, but in that case, it's still not being created or destroyed. It's just changing in form from mass to energy. So leaving aside the conversion to mass, energy itself cannot be created or destroyed, only changed in form. Another way to state this is the total energy of an isolated system must be constant. A system that cannot exchange energy in some way with its surroundings, the energy must be constant. Obviously, if it's a non-isolated system, the energy can change because it can always pass energy to something else. So that's why we say it's the total energy of an isolated system must be constant. Mathematically, change in energy of the system is equal to zero. There's no change in energy of an isolated system. Things can happen inside the system. The energy can be converted to some form or another, but it totally remains constant. And there's lots of forms of energy. The kinetic energy of air particles can be transformed by wind turbines into electrical energy, nuclear energy, hydroelectric energy, solar energy. These are all different ways that, all different forms that energy can take. And we'll talk about a number of them in the class. Okay, so bookkeeping number one. The total energy of an isolated system is constant, but we're usually not dealing with isolated systems. We're dealing with systems that can interact with their environment. So what we do is we take the entire universe and we usually partition it into two things: the system, the thing that we really care about, and the surroundings, everything else that acts in our system, but we're more interested in what's happening to the system. So if the energy of the system is not equal, then it exchanged energy with its surroundings, because we say that the system plus its surroundings is an isolated system, and therefore the sum of the change of the energy of the system and the change of the energy of surroundings has to be zero, or another way, just rearranging it, that whatever energy the system gains, the surrounding loses, and vice versa. So we usually don't care about precisely what's happening in the entire universe. We don't care about most of it. We care about what's happening in our plant. We care about what's happening in this stream. That's what we care about. So an important thing that we do in a lot of cases, and sometimes it's done sort of without thinking about it, is divide things into a system and surroundings. And that's one thing that can go wrong when you're setting up a problem. If you don't explicitly note where the division between the system and the surroundings are. If in one part of the problem you make one assumption about what's the system and what's in the surroundings, and in another part of the problem you make a different assumption, and then you start to have losing track of energy because you're not doing the bookkeeping right. Yeah, so what this is just saying is if the energy system changes, it must have gone into or come from the surroundings. It can't be anywhere else. So you can divide the system and the surroundings in any way that's convenient. It's true for any division, just some are more convenient than others. Yeah, you can divide it any way. You can divide the system and the surroundings in any way that's convenient. It's true no matter what you do. All you're doing is sort of drawing an arbitrary line in an isolated system. So any way that's convenient. Sometimes the system is the chemicals of the beaker and the surrounding is the beaker and the rest of the universe. Maybe it's different. Sometimes the system is the chemicals and the beaker, the surrounding is the rest of the universe. And it really depends on just how you're setting it up. So it doesn't really matter as long as one, you're consistent, and two, it's easy for the problem. And we'll talk about that when we talk about certain problems.